Composite resins are one of the most commonly used restorative material in clinical practice in dentistry. In this lecture, we'll be learning about the different methods for curing a composite resin. Light curing units are of different types, which basically aim at converting the resin monomer into a polymer. So for light activated composites, the conversion from a paste to its solid form depends upon degree of conversion, or in simple terms, how much amount of resin monomer has been converted into its polymeric form. Degree of conversion depends upon the ability of light to penetrate, access, and initiate curing in all parts of a restoration. Or rather, degree of conversion basically determines the depth to which a resin is cured. We have different light sources for curing a composite resin, which includes UV light, visible light, laser light, etc. If you take an example of a UV light, they basically act on an initiator named benzoyl methyl ether on a composite resin, which will be converted into free radicals. Whereas in case of a visible light, they will be acting on a photosensitizer named camphoroquinone, which is available at the concentration of 0.2%, which will in turn act on an initiator dimethyl aminoethyl methacrylate. And this activated photosensitizer and initiator combination will in turn generate free radicals. And generation of free radicals is mandatory for converting the monomer into its polymeric form. Camphoroquinone, as I just mentioned, is the most commonly used photosensitizer that absorbs blue light with wavelength ranging between 460 to 480 nanometer. Aim of any curing lamp is to provide the maximum light energy or intensity with a wavelength corresponding to the absorption range of a photo initiator in the composite being cured. So being the most commonly used photosensitizer, camphoroquinone, its maximum absorption range is in the range of 460 to 480 nanometer. So any light curing lamp which provide maximum light intensity at that particular wavelength range will be very effective in degree of conversion. Now let us see the different curing units or curing lamps that have been used or from the beginning of dentistry, and we'll also have a look at the latest advances. Quartz tungsten halogen lamp, or commonly named as QTH lamp, they have, from the name itself, we know the components. They are having a quartz bulb with a tungsten filament that will irradiate both UV and white light, and therefore it requires a filter because we don't need white light for curing composite. So a filter is also present which will remove the heat and all wavelength except those in the violet blue range, which is the wavelength we require for curing the composite resins. This is a picture of a QTH lamp that is being used in clinical practice. So as you can appreciate from the picture, we are having a light tip through which light will be coming out. This is called the light pipe. Then there are filters which will remove all light except in the range of the 460 to 480 nanometer. Then we have what is called a light guard, which will protect the eyes of the clinician from the UV light that is being passed through the light tip. Then inside the QTH lamp, there is a cooling fan to dissipate the heat that is being generated. Then there is the circuit board, and then there is a trigger switch upon switching on, which will produce the light through the light tip. Okay. So again, these are the components of the QTH lamp. We have a bulb, a reflector, a cooling fan, a filter, light guide, light tip, light guard or shield, circuit, and a trigger switch. As I mentioned before, a light shield is supplied to protect against direct observation of high intensity light by the clinician. It contains a bulb with a tungsten filament and it is filled with halogen gas. So when the unit is plugged in, the power supply will heat the tungsten filament within the quartz bulb. Light produced by the bulb or filament will be reflected by the reflector positioned just behind the bulb. This is the reflector that we just mentioned. And to eliminate unwanted wavelength, we also have a filter which will eliminate the unwanted light and they will be converted into heat. So those all unwanted wavelengths of light will be converted into heat, and this heat will be dissipated by the inbuilt cooling fan within the unit. Generally, QTH curing lights function in the range of 300 to 1200 milliwatt per centimeter square. Okay. And a typical QTH bulb is rated for functioning 80 to 100 hours, which comes to approximately 2.5 years of average clinical practice. And under ideal condition, they may last for more than up to 2 to 3 times than the mentioned time. So that is with QTH slab, no longer used because of its various drawbacks we have discussed just now. Like, and the clinical usage time is less when you compare with the latest advances, the need for using a fan to dissipate heat. So all these were certain drawbacks that the clinicians noticed. So the next generation curing lamp were named as plasma arc curing lamp. Plasma arc curing lamps uses a xenon gas under pressure that is ionized to produce a plasma. And they contain two tungsten electrodes which are separated by a small gap between which a high voltage is generated. So the resulting spark will ionize the xenon gas to produce an electrically conductive gaseous mixture of ionized molecules and electrons, which are basically known as plasma. Okay, so you have two tungsten electrodes which are separated by a gap, and within that gap, a high voltage is generated and a spark will be formed. This spark will ionize the xenon gas present within the system, and they will produce what is known as plasma. And plasma is basically a electrically conductive gaseous mixture of ionized molecules and electrons. And this unit will produce high intensity white light which can polymerize composites within 6 to 10 seconds. So one advantage of plasma arc curing lamp is it's because of its high intensity, the curing time is reduced. This is the picture showing a plasma arc curing lamp. Now, even though I mentioned it as an advantage, that is the rapid curing, actually, because of its high intensity and rapid curing, we end up having a rapid polymerization. That is, the monomers are converted to polymers at a rapid pace. Therefore, as a drawback or as a side effect of this rapid polymerization, we will be experiencing what you call as polymerization shrinkage stress, which is not a desirable property to have. And the equipment is quite large and it's expensive. And also because of its high intensity, there is an increased pulpal temperature, which can eventually result in pulpal damage. The next generation of light curing units are named as light emitting diodes. They basically use a solid state electronic process or NP type semiconductors. These light sources will emit radiation only in the blue part of the visible spectrum, that is between 440 to 480 nanometer, which is in the absorption range of camphorquinone, which I mentioned in the first few slides, which is the most commonly used photosensitizer. So since these light emitting diodes emit radiation only in the blue part, advantage is that there is no need for any additional filters to remove unwanted light. And LEDs also require low wattage. They can be battery powered. There is no generation of heat, and they're quite in working. There is not too much of noise because there is no inbuilt fan within the unit. Okay, and they produce the lowest intensity radiation, and hence there is no issue of polymerization shrinkage stress as well. So if you want more intensity in certain composite resins and the manufacturers may recommend using more intensity, then you can actually use 1 or 2 units of LED to LED units to cure the composites. Okay. So the advantage is being there is no need of filters to produce any blue light. The lifespan of LEDs units are up to 10,000 hours. They undergo very minimal deterioration with time. The units are small, portable, and very quiet. And they since they work on batteries, their power consumption is also quietly. The only disadvantage being its narrow spectrum of wavelength, but it can be managed, as I mentioned before, by using multiple units. This is a picture showing a LED curing lamp. The next generation of curing lights are called as argon laser curing lights. So these are basically using laser light and argon lasers are used. They have the highest intensity and they emit at a single wavelength. And lamps which are currently available emit light at a wavelength of around 488 nanometer. The advantage of argon laser curing light is its increased degree of polymerization and its greater depth of cure. And lasers offer uniform polymerization even if light guide is at a distance from the composite material. And therefore curing time is also because of its high intensity can be reduced to below 10 seconds. Disadvantage of using a laser unit is because one disadvantage that adjacent restorations or adjacent tooth may also be affected by the laser light. Because of its high intensity, there is a chance for rapid rise in pulpal temperature. There is also a chance of increase in polymerization stress, and also the cost for initially setting up such a laser unit is also on a higher side. So those were the common light curing units that have been used for over a period of last few years. First is the QTH lamp, then we have the plasma arc curing lamp, then we have the argon laser lamp, and then there is the LED curing units. Okay. Now let us have a look at what we mean by degree of conversion, which we mentioned in the first slide. It is the measure of percentage of carbon-carbon double bonds that have been converted to single bonds to form a polymeric resin. So amount of double bonds that have been converted to single bonds are referred to as degree of conversion. So higher the degree of conversion, better will be the strength, wear resistance, hardness, as well as fracture toughness. Factors affecting depth of cure of composites are, so as I mentioned before, you cannot have a standardization for all types of composites. There are various factors which will be determining to what depth or to what level the composites are being completely cured. First factor is the quality of light source. See, as I mentioned before, polymerization is initiated when a critical concentration of free radicals are generated. And for generation of free radicals, a particular number of photons have to be absorbed by the initiator system, which in turn is directly related to the wavelength, intensity, as well as time of exposure. Now, wavelength means as the wavelength should match the wavelength absorption range of the photosensitizer being used. So, if the composite manufacturers are using camphorokinin, then the wavelength of the light curing unit, its maximum intensity must be at the range of 460 to 480 nanometer. Next is the intensity and time of exposure. Intensity and time of exposure are expressed using two terms. One is radiant flux, other is radiant emittance. Radiant flux is the number of photons emitted per unit time, and radiant emittance is number of photons emitted per unit area. So the amount of photons that are emitted per unit time and also the number of photons that are emitted per unit area are very important factors which will affect the degree of conversion. Next factor determining the depth of cure or degree of conversion rather is type of composite. See, as I mentioned before, there cannot be a standardization for all types of composites. For example, darker shade composites or composites having more opaque components will require longer curing time because they absorb more light and transmit less light. So the depth of cure will be very small. And also, small filler particles will interfere with light and they will maximize scattering. So, in this such situations, we'll have to modify the light curing. Under optimum light curing conditions, the depth of cure is found to be 1.5 to 2 millimeter from the surface for a conventional composite resin and between 4 and 6 millimeter for a bulk fill composite resin. So if someone asks you what is the depth of cure under ideal condition for a composite resin, normal conventional composite resin, the answer is 1.5 to 2 millimeter. And for bulk fill composite resin, the ideal depth of cure is 4 to 6 millimeter. Next factor determining the degree of conversion is the distance from the curing tip to composite resin. That is, this distance between the tip of the unit and tooth surface. In simple terms, the tip of the curing unit must be as close to the tooth surface as possible. That is the simple answer. And if somebody is asking you a value, then ideally the curing tip should be at a distance of 1 to 2 millimeter from the composite surface to be effective. As distance increases, the intensity also decreases. So the curing tip must be as close to the tooth surface as possible. And also in inaccessible posterior areas, we can use curing units with smaller tips because using larger tips it will be very difficult for the clinician to take that curing unit to that area. Now, next important factor to be discussed while you talk about curing units is regarding polymerization shrinkage stress. Okay, so in order to compensate for this polymerization shrinkage, various variations have been advocated by various researchers. That is, certain modifications can be done the way you are curing the composite to compensate for the polymerization shrinkage stress, which includes first one is soft start curing, second one is rammed curing, and third one is delayed curing. That is, you're not curing the composite in single intensity in one go. You are actually modifying the intensity of the light as well as you're modifying the duration. Now let us see what it actually means. Just remember these three terms: soft start curing, rammed curing, and delayed curing. So these are basically different modes of light curing. Now, in soft start curing, what they're basically, what the clinician is basically doing is that the curing of the composite will begin at a low light intensity and it will be finishing with high intensity. So what is the advantage of starting with a low intensity and then finishing with high intensity? We are basically extending the time available for stress relaxation before reaching the gel point. I'll explain it again. See, in soft start curing, the curing will begin at low intensity, for example, 300 milliwatt. So the curing will progress, and it will reach gel point. Now, gel point is the point beyond which further hardening will take place. So when it reaches that gel point, the intensity will gradually increase, and therefore the curing will finish with high intensity. So actually, you are giving time for the composite resin for stress relaxation. So this soft start curing will allow for a slow initial rate of polymerization and high initial level of stress relaxation. So initially, since we are curing at very low intensity, we are actually giving time for the composite for high level of stress relaxation. And the curing will end at maximum intensity once the gel point has been reached. So this will drive the curing reaction to the highest possible conversion only after much of the stress has been relieved. So before reaching the gel point, much of the a large amount of shrinkage stress has been relieved by the composite resin, and only then the maximum conversion takes place. So that is the advantage of soft start curing. So the variations of this technique include rammed curing and delayed curing. So basic principle is you begin with low intensity and finish with high intensity. And the variations of this soft start curing include rammed curing and delayed curing. What do you mean by rammed curing? In ramming, the intensity is gradually increased or ramped up during the exposure. And this can be done in a stepwise manner or in a linear manner or in an exponential mode or in an oscillating mode. And what do you mean by delayed curing? In delayed curing, the restoration is initially incompletely cured at low intensity. So what do you mean by incompletely curing it? By incompletely curing it, we are actually giving the clinician some additional time for sculpting and contouring the composite resin to correct the occlusion and its features. And then a second exposure of light will be applied for its final curing. So this delay will also allow substantial stress relaxation to take place. The longer the time available for relaxation, lower is the amount of residual stress. So that is it with curing of composite resin. We have discussed till now the various light curing units for composite resin, which include QTH lamp, plasma arc, argon laser, and light emitting diodes, and the various factors determining the depth of cure, the degree of conversion, and also towards the end of the presentation, we discussed about the different modes of curing, which will actually help in decreasing the amount of polymerization shrinkage stress. Thank you.